So, hello everyone. So, today we would be discussing a paper pertaining to intermittent computing and energy harvesting. So, there's many different papers in this domain, and today we're going to address a paper which kind of focuses on a kind of paradigm which the researchers have suggested that's called what's next. So, oops. This paper is called What's Next? Intermittent Computing Architecture, and it's been worked upon by researchers from the University of Toronto and the University of Wisconsin-Madison. So today we would be discussing what this paper is about and what are the different benchmarks they have tested it upon. So a quick introduction to the terminologies that we would be encountering throughout the paper. The first is intermittent operation. So in very simplistic terms, it means when the power is not continuous. So it kind of refers to a process or system that operates with pauses or breaks in between periods of activity. So for us, these would be systems or programs that do not run on a continuous power supply. So they kind of run on a power supply that's intermittent, or you're gonna have power to the program and then you're gonna lose power to the program. So it's kind of different than the usual um, program execution. The next term is energy harvesting. So energy harvesting is the process of capturing and converting various forms of energy from the surrounding environments into usable electrical energy. Now, this harvested energy can be stored or directly utilized to power electronic devices or systems. So it's basically energy wherein traditional power sources like batteries or grid electricity may not be useful. I mean, it's for these niche applications where your traditional energy is not good. That's where you need energy harvesting. The next is state persistence. So state persistence refers to the ability of a system or an application to retain or remember its current state or data even after it has been shut down or restarted. So for us in computing, the state refers to the collection of data that represents the current condition or configuration of a program. So this might include variables, this might include some boot up settings. This might include register values, interrupt vector table, etc. And the last part is program consistency. So program consistency refers to the property of a computer program or a system to maintain a predictable and reliable behavior under varying conditions and inputs. So we can say that a consistent program is a program which behaves in a manner that aligns with user expectations and system specifications and producing reliable results, maintaining data integrity. So we would be focusing our research on these four topics and how we can better these. So jumping on to what's next. So what's next is what they call as the name of their architecture. And the goal of what's next is to provide a partial answer when the energy is scarce, but offer the flexibility to refine that answer if more energy is available. So in that sense, the authors kind of extend the anytime automation model, which provides like early approximate version of the application's output. And then as the application continues to run, it refines the output towards a precise result. So basically, the common characteristics that the what's next architecture targets is that it should be subjected to non-trivial checkpointing, recovery, and re-execution overheads due to frequent power outages. The load should be, or the target program should be amenable to approximation, and it should contain a many-word granularity integer and fixed point operations that are costly in the usual ultra-low power processors. So since your energy harvesting devices operate under the intermittent computing paradigms, they incur frequent power outages. And hence, to enable forward progress despite these frequent power outages, these systems use non-volatile processors or periodically checkpoint to non-volatile memory. So in that sense, anytime automation also uses interruptibility and flexibility. So in this paper, the researchers propose like two algorithms, but before jumping into them, let's kind of focus on what this figure means. So in this example, let's say a conventional energy harvesting system wherein the device resumes processing each input after a power outage until the final result is achieved. So input F arrives while the device is still processing input D, and that is something which can kind of cause idempotency errors. So in this case, when a power outage occurs, um, you may never know where your program is. But with the what's next paradigm, whenever a power outage occurs, an acceptable result is already available for A, and we can begin processing the next available input when power returns. So this, as a result, we start processing the input F soon after it arrives and achieve greater forward progress across all the input samples. So in crude terms, this means that in whatever resources or whatever time I have, I try to calculate some fraction of the output. And then I kind of check if this fraction of the output is satisfactory to the complete output. And then after every forward progress or every forward iteration, I go on improving my own result. So as more and more iterations run, or as more and more energy is supplied, my output refines itself. And that's basically the idea behind anytime automation and precisely what's next. So in this paper, the authors implement two subword-based modifications. One's called subword pipelining, which decomposes high latency instructions into smaller operations, and subword vectorization, which kind of fuses low latency instructions such that the most significant subwords of the different data elements are processed in parallel. And of course, to add, and of course, complementing these two is something which the authors called skim points. And these skim points are nothing but checkpointing schemes. There is a backup operation which saves the current program counter to non-volatile memory. Then during a restore, the system resumes at the saved program counter and continues executing. So skim points kind of decouple the backup program counter from the restore program counter to allow pre-processing to skip the remaining subwords if an acceptable result is available and start processing new data. So skim points is basically if you have a fast forward in your video. So coming behind the motivation of this paper, so in the figure, we have an output which shows the precise implementation when it loses power halfway through processing the image. So your figure A is the baseline, which is when it's running at 100% runtime. B is the baseline when it's running at 50% runtime. So basically, your power is just gets lost in between your computation, and that's what you get. It's just half an image. And C is if you use what's next. So even in the fraction of time which you get, you try to compute the final result or a fraction of the final result. And so whatever you get when you lose power is kind of like a unrefined version of your output. And that's exactly what image C is. So it's kind of like a blurred image of uh, maybe sub-image A, but it kind of gives you a good idea as to what the whole motivation behind what's next is. So with anytime processing and the same total power on time, we can compute a result for the entire image with the forward computations. And so then we need to focus on how anytime processing compares to input sampling. So energy harvesting devices, which usually operate on a continuous input signal, can sample those can sample those inputs if the processor is not able to keep up. But sampling with precise computation is not really desirable since it requires much more precision, and if you lose power in between, then you kind of don't know where you exactly are. So rather than having precision, it's important that we generate an approximate output for a large number of inputs. So if in this case, let's consider like both these examples are like blood glucose monitoring for patients suffering from diabetes. So regular monitoring is required to detect dangerously low levels, prompting corrective action whenever the levels go very much low. So usually energy harvesting devices are good applications since they can run on intermittent energy. But these devices must be careful since collecting readings at intermittence also requires a high amount of accuracy. Now, in this figure, the dotted line shows the data collected in clinical settings at 15-minute intervals over a 10-hour period. Now, these dips indicate periods of critically low blood glucose. Now, quickly and correctly identifying these dips is critical for the successful management of the disease. Now, the input in this figure, in the A part of the figure, produces precise results, but misses both critical events due to infrequent sampling. Like you can see that the green square is your sampling. And so whenever your glucose level is hitting a low, which is at 1424, or maybe between 18 and 1912, it's not exactly it's missing those points. And this is exactly something that can be dangerous when it comes to monitoring blood glucose, because now your program is kind of malfunctioning. But if you use anytime processing, which is your B diagram, then in this case, you can see that the anytime readings always catch these dips, which is the dip at 1424 and the dip just after 1800. So you can see that in this case, your blocks or your squares are much more consistent compared to your continuous curve. And that is exactly what we mean by anytime processing when it kind of aids your input sampling. So the resulting energy saving also allows to process more readings, which as a result lead to catching these critical events. Now, coming to the architectural part of this. So the anytime architecture has been divided into three parts by the authors. So one is called the subword pipelining, the other is called subword vectorization, and the third part is skim points, which is kind of like a fast forward button in the program. And perhaps the whole idea behind what's next is that if sufficient energy is available, then we work towards a precise answer. But if not, then we accept the current approximation and move on to processing the next sample. So it's like rather than wasting time, if we have something which is kind of satisfactory, then let's assume it and go ahead. And the whole research is about how this is essential when it comes to certain tasks. So we'll discuss all of these in detail in the next slide. So first we'll focus on SWP, which is anytime subword pipelining. So anytime subword pipelining breaks long latency operations like let's say fixed point multiplication into subword stages, starting with the most significant subword. And then the approach splits each word into smaller subwords to be processed from most significant to the least significant. So if we look at the figure, then the A part of the figure is our conventional processing, in which case your word one is computed or the processing of word one is done, and then sequentially word two is done after word one is complete, and then word three is done after word two is complete, and so on. But with anytime subword pipelining, we can divide the word into individual chunks. And so in B part of the image, you can see that a chunk of word one is computed, then a chunk of word two is computed, then word three is computed. And now once we have these fractions of the words that are computed, you can check if the output that you receive, that is this specific line, is it comparable to your final output? And if it is satisfactory, then using skim points, you can just directly put it in the output buffer, or you can just directly declare that, yes, that's the output. So in this case, you kind of save energy on the next cycles. So in this case, let's say if you get a satisfactory result after, let's say, processing two words, then you just directly skip to the end. And that's exactly what subword pipelining means. It's that dividing a huge word into multiple subwords. And so we need to assess when we can use this and what are the constraints. So which computations are candidates for subword pipelining? So in general, any computation can be a candidate for SWP if it satisfies these two conditions. The first being that it incurs long latency, and the second being that it is distributive over addition. Now, the first property is not really necessary for correctness, but is desirable to reap performance gains. But the second operation is extremely important because this property is a requirement for guaranteeing that the precise result is reached once all subwords have been processed. And not only that, but this also guarantees that whatever output you're getting at the end of, let's say, at the end of a skim point is somewhere a fraction of your actual output. And this property can only be satisfied when when your computation is distributive over addition. So if you see in figure 5, you either have your function f, which can be calculated as a whole, or you have the b part, which is your function f is divided into subparts, and then we process the most significant bit of both A and B and store it in X and store it in Y. So as long as these step outputs are stored at the same memory location as the final output, you are always going to get an output at the end of every cycle. The next being how much programmer intervention, sorry. The next being how much programmer intervention is required. So since software support for anytime SWP is implemented entirely in the compiler's intermediate representation, we need minimal changes in the source code. So you can see in listing 1 that we only have the ASP pragmas, and these are what define your input and output memory locations, which is nothing but IR. So for each input, the programmer specifies the subword size, which is 8 in this example, and then computations in the IR that satisfy these two properties are transformed to enable subword pipelining automatically. So in this case, the computation F is multiplication with some array element, capital F of I. So it's basically dividing this array into smaller arrays. And that's what algorithm 1 does, is that it provides a high level description of the compiler paths we need for SWP. And if the operation's input and output operands are annotated with a pragma directive, then the operation is marked as a target for SWP. So the loop is then split with a simple loop fission compiler pass, and the loop is split twice for the 8-bit case, which is the case for us, like in listing 1, and it is split 4 times for the 4-bit case. So the long latency operation in each loop instance is modified with its anytime equivalent. So we would see that in the next slide, wherein we have mul underscore ASP8, which is precisely a modification of the multiplication operation. So to support the subword pipelining, these are the subword variants of long latency operations. Like mul underscore ASP8 is kind of a variant of the mul operation. And the syntax for this is that you first define your operation, which is either mul, add, etc. OP underscore ASP. ASP denotes anytime subword pipelining, and then you specify what your size of the subword should be. So in this case, it is 8-bit, but it can also be 4-bit and other sizes as well. So this is how we kind of define an action here. And then R4 and R5, the usual destination registers. And then we just have your one statement, which is like indicating that you need to go with the main most significant bit first and then the least significant bit. So you can see that the mul ASP8 is kind of repeating in both of this. First for the loop for the MSB, which is your main, like the most significant bit, and then again for the least significant bit. So this is nothing but an assembly code of what was in listing 1. And so this gives us like a brief idea of what SWP is. The other algorithm that they propose is called SWV, which is called subword vectorization. Now, anytime subword vectorization transposes short latency operations, let's say like addition, so the most significant subwords are processed first. So in contrast to anytime subword pipelining, where a single data element is split into subwords, in anytime subword vectorization, Subwords from multiple data elements are processed in parallel. So thus we generate an approximate result for several words in a single cycle, thereby gaining a speed up over the baseline implementation. And the target operations are bitwise operations such as AND, or NOT, XOR, etc. So you can see in figure 4C that in a conventional processor, we have one word which is being processed, then you have word 2 which is being processed, and word 3 that's being processed, and these go from most significant bit to the least significant bit. So with the SWV, you have your diagram D, which has a part which is the most significant bit of word 1 being processed, but the same most significant bits of word 2 and word 3 are also processed parallelly, like it's vectorization. And then at the end of your function, you have your skim point, which then checks if it's an approximate version of the output. And if it is, then it directly fast forwards to the output. So in a way, this is similar to what SWP does, but SWV is just parallel computation. And so this definitely has a higher speed up than SWP. So just like SWP, SWV, we should also have computations which are ideal candidates. So for this, the authors have defined a star operator, and the star operator is something which means that we can only vectorize operations where both operands can be decomposed into subwords. So basically, if any of the computation follows this particular equation, then it is an ideal candidate for SWV. And that is what's being kind of indicated in figure 6, which says that, let's say you have A and you have B, and you have the star sign. So the most significant of A, the most significant of B, and also of C and D, all of this can be sent to your star sign at the same time to get the output. Like before, you had A and B, and which compute X, and then C and D compute it after that. But with subword vectorization, all of the most significant subwords of all the words can be processed at the same time. Now again, we see which microarchitectural support is needed. So for this, we have the pragmas which are very similar to SWP. You have your add underscore ASV8. So ASV stands for anytime subword vectorization, and then you have your operation before the underscore, and then you have your subword size at the end, which is 8 in our case. So listing 3 is your program, which is vector addition. And the one to the right-hand side is the assembly conversion of that same program. And so similar to SWP, SWV also requires minimal programmer intervention in the sense that the programmer only needs to mention these pragmas in the program, and the rest of the stuff would be done by the compiler. So especially one thing that we focus on with SWV is provisioned addition. So subword vectorization of logical and memory operations does not kind of require any new instruction or changes to hardware. The compiler can simply use their full precision equivalents. So let's say we take an existing 32-bit adder unit and reconfigure it with a straightforward modification to support 4-bit and 8-bit parallel subword operation, while still maintaining support for full 32-bit additions. So at intervals of every four full adders, like 1 bit, a mux is inserted into the carry chain, which is shown in the figure, which is this particular mux. So for example, if we have the subword size as 8, then there should be a mux between bits 7 and 8, 15 and 16, 23 and 24, etc. So what this does is these muxes give greater forward accuracy. But while inserting these muxes, it also increases the overall latency of the adder because now you have another component inside it. But we expect this to have no significant impact on processor frequency. And now we focus on skim points, which is like the final component of what's next. So I think we already discussed this before. Skim points are nothing but fast forward blocks. So skim at the end of, like whenever you are going to lose power, you hit the skim point, and then the skim point saves your data. like whatever output you have generated with that subword to your main output location and checks if this is a satisfiable output which we need. And if it is, then it just fast forwards your computation to that without actually refining it further. And so skim points, like the main function of skim points is to further the speed up. So it's kind of a mechanism for decoupling the checkpoint location from the restore location. Discussing the methodology. So the authors apply what's next to both volatile and non-volatile processors. And they use the simulation infrastructure, which has the ARM M0 Plus CPU simulator, which contains a two-stage pipeline, no branch predictor or cache, and implements an iterative multiplier that takes 16 cycles to compute a 16 by 16 product. Now, the ARM processor supports a maximum frequency of 48 megahertz, but due to the tight energy budgets of energy harvesting devices, we typically run at lower frequencies, like 24 megahertz. And the simulation methodology is that the simulator takes as input a 1 kilohertz voltage trace, which is captured from a Wi-Fi source, and we model a 10 microfarad capacitor as our energy source. So every time you get your energy from the RF, your capacitor is going to get charged, and then this capacitor is going to discharge, and this discharge is what's going to provide you the power. So it's basically an RC circuit, and the power you get is kind of um, a inverted exponential function. Now, since it's kind of a paradigm, you need benchmarks to assess it. So the authors have used a couple of benchmarks which they use to um, convince us the results of what's next. So they use 2D convolution, matrix multiplication, matrix addition, home monitoring, data logging, and location tracking, which have different domain areas, and they have its description. And this fourth column, which says the INSN percentage, is the percentage of instructions that are amenable to what's next. Like these are the dynamic instructions wherein what's next can be used. And since it's a program and it's a benchmark, we also need to have an error metric to determine how accurate that is. So we use the normalized root mean square error as our quality metric. And since acceptable quality is inherently subjective, we present error curves to demonstrate the runtime quality trade-offs. So these error curves will be discussed in the next part of the slides. Exactly. So we define the evaluation based on 5 parameters. The first is a runtime quality trade-off. So this figure shows the runtime quality curve for the applications, wherein each figure shows the curves for 4-bit and 8-bit subwords. And so in all cases, you can see that quality improves as the application progresses until the final precise output is reached. Also, an approximate output is available early, allowing the application to terminate early. However, what's next techniques incur runtime overhead to reach the precise output. And this is due to the presence of other instructions that are not amenable to subword pipelining or subword vectorization. And hence they must be re-executed several times due to the iterative nature of the anytime what's next techniques. Like in this case, in figure 9C, you can have mat add with 8-bit subword vectorization, which has an approximate result, and it is available at only half of the baseline runtime. So terminating the application at that point would yield us a 2 times speed up with an error of just 0.8%. Thus, this is a very good example of how runtime quality trade-off can kind of be beneficial for our programs, because if we let go of quality, then we can have substantial speed up and decrease in the runtime. Then the authors use these benchmarks on volatile processors, and volatile processors essentially have flash memory, so they need periodic dynamic checkpointing. And so by employing SWP and SWV, we observe considerable speedups as it's mentioned in the diagram. So what's next yields average speedups of 1.78 times and 3.02 times, with errors of 0.36% and 3.17% for 8-bit and 4-bit subwords. So in this case, we can say that VAR, which is the home monitoring, improves performance by 3.02% with an error of just 2%. And in the best 4-bit case, the same program achieves a speed up of 4.69 times with an error of 9%. And then the skim points naturally eliminate high overheads, because if you have a sufficient approximation of the output, then you can just directly fast forward to your output. So naturally, we know that 8-bit subword pipelining and 8-bit SWV produce higher quality results than 4-bit techniques, while 4-bit techniques and vectorizations yield higher speedups. So this kind of uh, goes hand in hand with the theory which we had before even starting this research. Then the authors test this on non-volatile processors, basically the processors which have FRAM. And so in this and so for non-volatile processors, the processor's current state program counter register file is backed up every cycle. So effectively, the current progress of the application is automatically checkpointed when the power is lost. So similar to checkpoint-based processor systems, skim points allow the application to skip to the end of the current task and take its current result. So like this figure shows the speed up and error for all benchmarks on a non-volatile processor. And so the what's next techniques yield average speedups of 1.41 times and 2.26 times with 8-bit and 4-bit subwords. And so for this, in the best case, we have the matrix addition, which improves performance by 1.78 times for the 8-bit one and 3.44 times for the 4-bit one. So in general, we can see that compared to volatile processors, we observe higher speedups in volatile processors than in non-volatile processors. And this is kind of expected, as the checkpoint-based processor incurs greater re-execution overhead than the non-volatile processor, which saves state automatically. This what's next, which produces an approximate output sooner, avoids much of the re-execution overhead incurred by checkpoint-based systems, leading to greater speedups on these systems. And this is exactly a good advantage which what's next gives, and which is kind of counterintuitive. The next is an area and power analysis. So this is taking into consideration the Synopsys design compiler version, and it kind of compares like energy harvesting devices were manufactured at 90 nanometer scale, and the authors used the TSMC as a 65 nanometer process technology. So just to give a brief high-level overview, we obtain an Fmax of 1.12 gigahertz in this. And since we are using muxes for the provisioned addition, we have the muxes in the carry chain, which incur an additional 0.02% area overhead compared to a Cortex M0 Plus CPU, which is implemented in 65 nanometers. So the addition of the muxes increases the power consumption of the adder by 4%. And then we have design exploration, wherein we explore various different designs which can be used to enhance this. So the first being combining vectorization and pipelining. So the authors kind of figure that SWP and SWV are orthogonal, and you can use both of them or combine both of them in a specific application. So it's like applying SWV to MATMUL produces approximate outputs which are 1.08 times and 1.24 times earlier than without vectorization for 8-bit and 4-bit subwords. Another design idea is memoization. So in this table, you can see the results for 2D convolution when the earliest available output is taken with and without memoization. So the speedups are shown, and you can see that memoization and zero skipping improve the speedup offered by subword pipelining from 1.7% to 1.97% for the 4-bit case. Similarly, they go from 1.31% to 1.42% for the 8-bit case. So naturally, the greater speedups for smaller word subwords is expected, as smaller subwords are more likely to be repeated often and therefore hit in the table, offering greater benefits for SWP. So naturally, in this case, we have we use memoization, for which we use the index into the table, which is the concatenation of the two least significant bits of both operands, while the lookup tag is the concatenation of the upper 14 bits of both the operands. Then we have the provisioned vectorization for addition. And so provisioned addition allocates extra space to alleviate overflow for computation that produce carry bits. But in this case, we cannot really, like the original 32-bit inputs are not likely to overflow. And since they typically do not utilize all the 32 bits. So this section is more or less about how provisioned vectorization is decreasing my error percentage, but it's kind of again increasing my runtime. But with subword vectorization, there is a higher risk of overflow since less significant subwords are likely to fully utilize all of their bits. Then another design idea is sublining with smaller words. So right now we had subword sizes of 8 bits and 4 bits, but the researchers have also explored subbit sizes of 3-bit, 2-bit, and 1-bit for SWP. And so the left figure shows the speed up relative to the baseline for the 2D convolution program if the applications were terminated as soon as an approximate value is available. And so you can see that the speed up for 1-bit and 2-bit is substantially higher than 4-bit, but obviously we also have a higher error percentage for those. So it's more like a trade-off between size of the subword and your accuracy for the program. Or it's more like your speed up and the accuracy of the program. Again, it's a runtime and error um, trade-off, but in the conventional processor, terminating the application halfway gives you a 2 times speed up. But this is unacceptable if you look at figure 2b, because then you don't really get an output that is an approximate version of your final output. So in short, one can say that the what's next techniques are effective in both non-volatile processors and checkpoint-based volatile processors, and they achieve average speedups of 1.41 times for 8-bit subwords and 2.26 times for 4-bit subwords. Then this is kind of the end of how exactly what's next is. So the basic idea being that you split your work into smaller subsections and you do operations on these smaller subsections and you get an output from these subsections. And then you see if this output is an approximate version of the satisfiable output. And if it is, then just stop operation, assume it as the final output and go on. And so there are a number of techniques that have been cited in the paper, and other techniques being hibernus, quick recall, and clank. All of these address the timeliness of outputs on energy harvesting systems. And so their work mines historical information from past inputs, which are retained in non-volatile memory. So it's about dynamic checkpointing. Then we have anytime algorithms. So we are kind of using anytime algorithms in this paper. And anytime algorithms are most applicable in applications which operate under real-time constraints, where lower output quality is preferred to exceeding time limits. So existing work kind of includes anytime automation on which this paper builds, and work that explores porting contract anytime algorithms to GPUs or providing CUDA and stuff like that. So that is what the other research on anytime algorithms is. And then reduced precision computation is also proposed in a couple of papers. And reduced precision arithmetic is specifically used in deep neural networks to trade off accuracy for more efficient execution, which is something similar to bit serial computation of reduced precision operation in order to achieve a greater efficiency. So that was about the related work. Now, in as a concluding statement, it's like in this paper, there's a novel technique for anytime approximation on energy harvesting devices, specifically through algorithms or ideas like subword pipelining and subword vectorization, which allows computations to dynamically process the most significant bits first. And then with the introduction of skim points, we can decouple the checkpoint location from the recovery location. And so together, these mechanisms allow applications to produce an approximate output much earlier than when it produces. So in a best effort manner, the application can continue refining the results towards the precise output. And when a power outage occurs, the application bypasses to the end and takes its current approximate result as is, which thus enables greater forward progress. So that was all about the what's next paper and what it means by the what's next architecture. So thank you so much.